Knowing those massive constraints, it's worth looking at the modern state of the standard. C++20 introduced a massive ergonomic improvement specifically for high-performance computing with proposal P00019R8. This brought us std.atomicref.
Oh, this is a big one. HPC developers faced a huge bottleneck for years. They process massive arrays of non-atomic data using extreme CPU vectorization and streaming. But occasionally, they need to do parallel concurrent updates on that exact same data.
Exactly. And before C++20, you either had to make the whole array standard atomic, which completely destroys your ability to use vectorization, or you paid the massive memory cost of popping the data back and forth.
So Atomicref comes in and allows you to apply a temporary zero-copy atomic view directly over regular non-atomic data. But I was reading the proposal, and there is a severe technical catch here that developers absolutely must understand before they use it.
There is, and it goes right back to the hardware. Because you are dynamically retrofitting atomicity onto a standard object, Atomicref demands strict hardware-level required alignment.
The cache lines.
Yes. If your underlying data is not aligned precisely to the specific cache line boundaries that the physical silicon expects for its atomic instructions, the hardware simply cannot guarantee the indivisibility of the operation, and the abstraction collapses entirely.
That's dangerous.
It is. Atomicref is a phenomenally powerful tool, but it essentially strips away the compiler's protective padding, exposing you directly to the microarchitecture's strictest alignment constraints.
And as we look to the 2020s and beyond, the biggest pressure on C++ isn't just wringing out more performance anymore, it's the safety debate.
The rustification of systems programming.
Right. With the meteoric rise of memory-safe languages like Rust, the committee is facing intense industry and even government pressure to solve concurrency safety at the language level. Looking at the current landscape, there are two competing visions for how C++ survives this.
The first one is from the creator himself.
Yes, you have Bjarne Stroustrup's vision of profiles. This is an opt-in model where developers restrict themselves to safe subsets of the language. The rules like preventing data races or lifetime violations are strictly enforced by external static analysis tools rather than modifying the core compiler itself.
And on the exact opposite side is Sean Baxter's Safe C++ proposal. This is a radical push to build a rigorously safe subset directly into the C++ compiler itself, highly analogous to Rust's borrow checker.
And the outcome of this specific debate will essentially define systems programming for the next decade.
Currently, the committee heavily favors the profiles approach. Their primary fear is that natively integrating a borrow checker would irrevocably fracture the C++ ecosystem, creating a hard divide between old C++ and safe C++ that code bases couldn't easily cross.
The governing ethos remains consistent with the 1990s. C++ exists to provide you the tools for safety, but it fundamentally refuses to mandate a single restrictive paradigm. So, bringing this all together, what does this actually mean for you when you sit down to architect a concurrent system tomorrow? The synthesis of this entire decades-long journey is the absolute necessity of what we call full-stack reasoning.
Concurrency does not, and mathematically cannot, exist in isolation.
A memory consistency model must align flawlessly from the high-level language abstractions you type, down through the compiler's aggressive optimization passes, translated into the specific instruction set architecture, and finally executed faithfully by the physical silicon of the microarchitecture.
Understanding this chronological evolution is the critical difference between a developer who blindly sprinkles memory order relaxed into their code, hoping for a magical performance bump, and an engineer who can formally reason about exactly why a lock-free queue behaves differently on an M1 ARM chip compared to an Intel by 86 server.
Trust the SC-DRF contract by default.
Absolutely. Write data race-free code, use standard mutexes or sequential consistency, and let the compiler guarantee your sanity.